what we are looking at is the user interface of Turbo Design 1, which is the 3D inverse design code, and we will use it to design the impeller wheel for the Sirocco fan. So for the baseline design, let me start by opening the impeller input file that was exported from the mainline code TD-pre. As you can see, all the specifications here, like the flow rate, RPM, etc., have already been filled in from the TD-pre file, and we can also see the meridional shape, which again comes from the mainline code along with this 2D grid, which is automatically created and can be adjusted using these options here. And the solver is actually a 3D code, and even though we don't have a numerical grid in the tangential or pitchwise direction, it solves the equations using discrete Fourier transforms, and that's why the code is very fast and is numerically quite efficient. Now we support different types of blade thicknesses such as normal and tangential, and in terms of type we have the simple constant thickness as well as complex distributions like Naka profile and flexible control points, but in this case we can go with a flat plate type constant thickness distribution as typically seen in Sirocco fans. And actually this possibility to specify thickness as part of the design process is very useful because it guarantees structural integrity, and if you have some thickness profile, then you can import that as well using this option here. Now sometimes the flow separation in these fans cannot be completely eliminated as a consequence of the trade-off between aerodynamics and packaging, and so the mainline code has also estimated the expected boundary layer blockage at the hub and shroud sections. And then we specify some fluid dynamic inputs, which is the blade loading, and this is the most important part for the inverse design process. Here we first specify the span-wise RVT star, which is the swirl distribution from hub to tip. So 0 span-wise location is the hub and 1 is the tip, and we are importing the span-wise swirl distribution at the leading edge and the trailing edge of the blade row, and the distribution is free vortex, so there is 0 swirl at the inlet, meaning a purely radial flow, and a constant value from hub to shroud at the outlet. And if you recall the Euler turbomachinery equation, then the difference in RVT star between the inlet and the exit gives you the specific work of the blade row. And this is important because it means that every design coming out of TD1 respects your required duty point. Now that the overall blade work is fixed, we need to specify how it varies from the leading edge to the trailing edge at both the hub and shroud sections. And for this, stream-wise blade loading, which directly controls the blade surface pressure distribution. This is basically the derivative of RVT star, and it directly relates to the pressure jump across the blade. So here we have a parabolic section from the leading edge to a point here that you can vary a linear section between these 2 points, and from this point to the trailing edge we have another parabolic section. The loading at this point defines the incidence at the leading edge, and at the trailing edge the loading is always 0, which satisfies the kata condition. And so with these 4 steps you can easily parameterize the 3D blade loading for manual adjustment or for automatic optimization. And of course the distribution is loaded for this baseline impeller. And then the last important parameter is the stacking condition. And so on one quasi-orthogonal at some stream-wise location, which is 1 or the trailing edge in this case, you actually specify the variation of wrap angle from up to tip, and in that way you can lean the blade, and this will create a span-wise pressure, force or gradient, and this is something that you can also use to additionally influence the 3D pressure field. But for now, we can continue with zero or axial stacking at the trailing edge, as commonly found in Sirocco fans. Now, even though the program is fully 3D, it runs very quickly within 5 seconds or so. And it gives you the blade geometry and also quite an accurate envisaged flow information. And this information is something that we can then use to iterate on the design. So we can first take a look at the converged rotor geometry using this 3D plot here. And then we can create 2D plots of, let's say, surface pressure at the hub and shroud. And we can also relate the isentropic Mach numbers and isentropic velocities to some performance parameters, which we can then use to explore the design space. And you can see these performance parameters here in the project manager window. Such as the indicators of diffusion and profile loss, and geometry parameters such as throat area. And under this UDP section, you can also use Python scripts to develop your own specific parameters. And then it's also possible to create a 2D plot of these parameters, such as the diffusion ratio. So now you can see the diffusion ratio value has appeared in the 2D plot for this baseline case. And the impeller design can be verified with the CFD or FEA analysis, and for this the geometry can be directly exported from Turbo Design 1 to different format files that are needed for mesh generation, such as curve files for TurboGrid or step files for ANSYS Mechanical. Now, sometimes when you take your baseline impeller through a CFD analysis, you might observe a negative incidence at the leading edge, resulting in flow separation on the pressure side. So for the first redesign, what we are going to do is to introduce a leading edge loading at both the hub and shroud, like this. And what this means is that we are imposing a positive incidence onto the leading edge. And once this is done, we can click Run again to get our first redesign. And then we can check the 3D geometry and 2D plot again for the first redesign. And we can rename this case as redesign 1. And then we can select the baseline case for comparison. So if we go to 3D plot first, we can actually combine the geometries and see how the leading edge angle has changed. from the baseline to redesign 1. And also if we look at the 2D plots, the introduction of leading edges is clearly visible in these plots, which have opened up at the leading edge. And also we can see in this 2D plot that the new diffusion value has appeared here for redesign 1. And there is actually a reduction in diffusion, which means that we already have a better design from the baseline. However, even with this redesign, your CFD results might show that the flow is not being guided as much as required due to a late turning of the blade passage. So the next redesign that we are going to do is make the blade loading distribution as 4 loaded for both the hub and shroud. And so all we need to do then is to make the slope negative at both hub and shroud like this. And you can see how the entire distribution has become 4 loaded. So with this change, let's run the design again. And now we have our redesign 2, which we can rename again. And we can go back to our 3D geometry, which we can compare with redesign 1. And clearly there is further change in the design, which is now showing more turning towards the front portion of the blade as expected. And also if you look at the 2D plot, then because of that blade loading change, the gap has actually increased in the front portion and reduced at the rear portion, thus confirming a 4 loaded design. And also if you look at the diffusion ratio, there is a further reduction compared to redesign 1. And so with all of these redesign steps, we have basically improved the diffusion on the blade, which is an indicator of the chances of flow separation. And we want it to be as low as feasible. So it appears that redesign 2 is a good candidate for a stage CFD analysis with the volute.